Welcome to this course on FPGA based signal processing systems. We'll continue with the simulation of this combinational logic circuits. The half-adder circuit which we had done in the structural model and the data flow model, also in the behavioral description. So we'll take this one of these modules, and then try to make this building the blocks of adder, right? Like half adder and then a full adder, or the half adder and full adder in a 4-bit adder. So, making one module and instantiating in the other module, and making the both of them in the other module also. So we will see the different levels of instantiating them in one module. So this is a half adder module. We had seen already this module, module n module. Half adder is IHA is the module name, input A, B, output sum and C out. So as given in the diagram. So the assign A XOR B is the sum, and assign C out A and B. This is a simple for carry. So this is a simple data flow model. This half adder module and the full adder module, we had already looked into full adder, which has 1-bit full adder, A, B and the C in. C in is the carry in, and the sum and C out are determined from the inputs. So module FA, module name, input A, B, C in, output sum, C out, and the assign A XOR B XOR C in. So this is calculating the sum, and then C out A and B, B and C in and A, and OR these two expressions in it. So you get, this is also a data flow model. So this model, these two models, half adder and full adder modules, will be used in the 4-bit full adder or 4-bit adder module. So 4-bit adder is can be, the block diagram can be visualized like this. So there is a half adder, that's the first bit. Suppose you have the A0, A1, A2 and A3, 4-bit, one number, B0, B1, B2 and B3 other number. So if we add both of this, what is the sum and what is the C? C out, we can say, just carry right now. And this sum will be 4 bits. So S of 0, S1, S2 and S3. So the first bit doesn't have carry in. Okay, so the half adder is sufficient for in the 4-bit adder. The first bit can be summed up with the half adder. So A of 0 and B of 0 are these two inputs. Okay, and the carry which comes out of this is C of 0. This is the one. Okay, if there is a carry, and this bit, the second bit, A1 and B1, also the sum C is 0 is sum 0, and the next full adder, next is a full adder, because if there is a carry in the first bit, that would also be taken to the full adder. So A1, B1, these are the two inputs, and C of 0, which is the carry from the previous bit, is a full adder. So this is sum 1, the output here. Also the next, similarly, A2, B2 is a full adder input. It is taking full adder taking the input A2, B2 and sum S2, this one, and if there is any carry from the previous bit, it is also considered here. Okay, so this full adder, the 1, 2, 3, 4, this 3, and this can give even a carry 0 or 1, and that is taken care in the 4th adder, that is full adder. A3 and B3 are inputs, C2 is input, another carry input from the previous stage, and then sum is 3 is the output, and C out is the last bit output. Okay, so from this 4-bit adder, we are going to instantiate it using the previous adders. So you can see the compiler directive hash grave ascent include, and within the bracket you give the path where the half adder module is installed or you kept there. So and then second one, it is also instantiating the full adder module, so which is also to give the complete path within the quotes with compiler directive include, and then module, and it's an end module. So the module name 4-bit add input, so A0, A1, A2, A1, A2, A3, so up to this 4 bits, and B0, B1, B2, B3 is 4 bits, and then output some 0, some 1, some 2, some 3, 4 bits, and the output here the C out is taken as carry if 4-bit addition gives any carry C out. So then this is a wire declaration, let's take it for later. And first instantiation, the first half order module, consists of the structural model in the first half adder, next full adder, another full adder, and another full adder. So the first instantiation is half adder HA. HA is the half adder here, HA dot V, and the name, optional name, that is HA0, this is a module name, instance identifier otherwise, and call us. So it's a module name, and A, B are inputs to the half adder, A of 0 and B of 0, the first bits are inputs, and sum of 0, which is the output, C of 0 is the output, the carry out from the half adder, first half adder. So now second we are instantiating the full adder, FA1, this full adder 1, this one, and the inputs are A1, B1, and in output from the previous half adder, that is carry, and sum 1, these 3 are the inputs, and sum 1 is the output, and C of 1, sum of 1 and C of 1 is also the full outputs of the full adder. Next full adder instantiation, module name again A2, B2, and this output from the carry output from the previous full adder, and the outputs the sum of 2 and C of 2. Okay, so this should be in the order if you are not mapping with the port name, that is dot port name. Okay, so with local variables, if you are doing it, that would also be fine, and if not, then follow the order in which it is used in the module. Okay, so this is why it is following the order. If first we defined it in the half adder and full adder, the inputs and then output. So similarly input and output. Next full adder, the third one, A3 and B3, the last bits of the inputs, and C2 from here, and sum and C out, sum of 3 and C out is the carry out which is coming out from the full adder module, the third one. So now the complete instantiation is over. Now we can see the wire C declaration. Wire C is 0, 1, 2. Okay, 0, 1, 2. There are 3 bits. So those are having this 0, 1, 2. Okay, so these 3 bits are combined and declared as C, because C of 0 is a wire which is connecting the first half adder output carry to the next full adder input. Similarly, C1 is also connecting in the first full adder output to the next full adder, C2 again connecting the second one to third. So this needs to be declared as wires like in the structural model. So otherwise it is this outputs are unknown. So the wire declaration is a mandate here. So module and the end module. So this is instantiating 2 different modules inside the module. So it's just to have only one half adder module and one full adder module, then we can multiple times the full adder module can be instantiated, and the one half adder module also is instantiated once. Okay, so you can see the instantiation of the calling the other modules inside the one module and multiple instantiations as well. So the test bench gives the module and a 4-bit adder test. Inputs are A and B, that is reg declaration. See the output again, the wire sum and wire C out. So these are the output, 4 bits and 1 bit. Now integer I and j, which is going to give you the different combinations of inputs we are going to generate. So this I and j declared as integers. Now this is used in the for loop, that is why so I and j are used in the for loop. Let's see, 4-bit, the next comes the after initialization, So, at the input output declaration, this comes the instantiation of the module, what we had, the 4-bit module which is we had written, and instantiating them 4-bit add here uut dot a dot b dot sum and dot cout. You can see in the order in which it is instantiated, and then here is the initialize this. Also we can have the initializing, what are the tasks to be done here, dollar monitor and dollar time, printing a b sum and cout. Okay, a b sum and cout needs to be are given in the order which is in the binary. This is to print on the console or in a separate log file. Okay, so the for loop, you can see the test bench uses the for loop I equal to 0, I less than 16, I equal to I plus 1. Okay, so this I is declared as integer before, and it is incrementing from initial value 0 to 15. Okay, because we have the 4-bit input. That 4-bit input can combination of A alone can be of 16 combinations, 0 to 15, and begin. So similarly B can have the 16 combinations, so we have to add all of them. That first A 16 combination and B 16 combination. So take A as one number and make all combinations of B, and then increment the A to second number, and then check for the sum and carry for the all other combinations of B, and so on. So for J 0 to again less than or equal to 16, 15, J equal to J plus 1. So we have two of them. So then begin A equal to I and B equal to J. This I and J are nothing but the inputs, 4-bit inputs itself. So then hash 5. So every 5 time units this gets incremented. I gets so first I is fixed to 0, then J is 0. After that 0 0 is assigned to this. After 5 time units J becomes 1. So A is still 0, B is 1. So after 5 time units this is 0, B is going to be 2, and so on. It will continue up to this loop will be continuing. This begin ends over here, the first one, and the second begin ends over here. So that's like within the brackets we write in the other languages, software languages. It is end and end, and it gives this end is here. Okay, so initial and begin end. So we have the monitor task, printing dollar time also. So it's A, B, sum and cout. So this 4-bit adder simulated outputs in the waveform viewer. So here we have given the A 0 to 3, that is 4 bits. You can see A is incrementing 0, 1, 2, 3. Okay, while A is incrementing B. So these are expanded bits of the A, that is 0, 1, 2, 3, A0, A1, A2, A3. These are the bits. And B 4 bits, you can see it is varying when A is 0 up to this point from here. So it is B is varying 0, 1, 2, 3, 4, 5, 6 up to 15. Okay. So similarly, when B is again incrementing here for an increment in A of 1. Okay. So this A of 2, it becomes again B is varying in this portion 0 to 15. Okay. So likewise, it goes up to this 15 combinations. Okay. So the exhaustive testing is done. So sum is equal to now this 0 and 0. So you get the same here at the first 15 up to 80 nanoseconds here. Next, this 1 is added with all of this. So 1, 1, 1, 1, 1 increment from 1 to 16 you can see. So this is shown in the radix X. So if you could see the radix decimal, and this would be 16 here. Okay. So similarly the 2 is added with this 0, 2, next is 1, 2 plus 1, 3, 2 plus 2, 4, and so on. It will be 15 plus 2, it will be 17 here. This is 17. So the expanded version of sum can be visualized here. Okay, so this is 0, 0, 0, 0, and 0, 0, 0, 1, 0, 0, 1, 0, and so on. So the cout is the final carry which comes out, so it is only popping up here. Okay, so at this point we 15 it exceeds, and then here 15 and plus 1, this is 16. So if in 4-bit sum you can have one carry here. So again here 2-bit, the here this is in two places the carry pops up, so and so on, and this carry can be seen at the different for combinations. So this I and j are also, so you can see them. I is 0, then j is varying from 0 to 15. When I is 1, again j is varying from 0 to 15. So similarly 2, I is varying from 0 to 15, and 3 and so on. So I and j are declared as integers, and default is, we didn't specify what is the bit size of I and j. Default is 32-bit. Okay, so 32-bit I and 32-bit j can be visualized in the waveform viewer as well. So this is a 4-bit adder. Actually, this is taking the previous bit carry and then proceeding into the next bit and so on. Okay, so this can be even to get the final bit sum and carry, it takes time. So when we do the timing analysis of this 4-bit adder, we can discuss the timing details in of this adder. So right now we have this as a combinational circuit with the data flow model, and the wire which is declared in between gives this so gives the structural model. So the 4-bit adder is developed using the instantiation of half adder and full adder modules. Now coming to the next, so that is another snapshot of this again. So you can see when it's 9 and 10 and 11, so the similar kind of outputs can be visualized also in the second one. The 4-bit adder, even in a log file we can generate them. Okay, with time 0, 1, 0, every 5 time units you can see the change in outputs. The first A is 0 for all up to this here, and then B is varying. You can just print those 0, 0, 1, 0, 1, 2, 3, 4, 5, 6 and so on in binary format, and what is sum and what is cout. Okay, so cout is 1 at this stage, it gives the carry here. So this is the log file which is printed, which is giving the, or you can print in the TCL console itself. Okay, so there are two ways to do that. So it is printing the output, so with the using the tab and so on. Also the complete cout up to 1000 it is time units, it is plotted. We can also plot it further. So next, this is about the full adder, and coming to the replication and the conditional operators. For example, so we have learned this replication operator, and this module name is replica. We had the input A, input again B is 2 bits, A is 1 bit, output C is 6 bits. So we are going to use both these operators to get to output C. Okay, so assign C, it's a data flow again, equal to continuous assignment. Within the curly braces you can see B, that is first, this is here we are given 2 bits, and 4 times A, this is a replication operator. How many times you want A to be repeated? So A is 4 times repeated, so this portion closes the replication operator, and then which is concatenated with B, that is in the again the curly braces. Note the curly braces which makes a difference, otherwise it will pop up an error. So replication and concatenation is assign C equal to B comma 4 times A. So let's see the output of this. C is 6 bits. The test bench replica test inputs in A, reg A, and 2 bit of 0 and 1 B. Output here is the wire C. Instantiate the replica here, replica UUT dot A dot B and dot C, 2 inputs and 1 output. Initial begin, what are the stimulus we are going to add it. So this is for time. Tab /T represents the tab, display it in a nice fashion. So /T B and /T C, so on. This is within the bracket. Okay, and then dollar monitor is a task %0t, it starts from 0, and T %B /T %B for dollar time and ABC. Dollar time is a keyword here. Okay, it's a task. Again, also the monitor. Okay, initialize this inputs A0, B0, and then wait for the global reset. Okay, so this comes under the initial begin. Hash 100. These details we have covered already in the previous lectures when we did the first simulation. Hash 100. Wait for global reset of hash 100, or that is 100 nanoseconds here. Add stimulus. Now hash 100, after 100 nanoseconds, A is made 1 and B is 2 bits 1 1. Okay, so 4 times A we need to get, and B is 1 1. Okay, so after that A is made 0 and 2 times that is 2 bits 1 1. Okay, so this is the replication operator. Using replication operator, A is made copied 4 times and B is appended with that. So similarly, A1 changed and B a different value. A is changed to 0, B is this, and N for every 100 nanoseconds. So N modules. Let's see the viewer, what is it giving. So here A is 0 initially. Okay, so B is also 0. So 4 times 0 here, and then 2 ones. Okay, so B is 1 1, and at this portion here A is 1. Okay, so 1 is copied 4 times. Okay, first 4 times, and then this is from here B next to 2 bits. So similarly this is 0, so 4 times this is copied 0, and the last 2 bits are from here. Okay, so this is the one which gets. So similarly here 1, that is 4 times copied, and the data change B is 0 over here. So here 0 0, we'll have this 0 0 from here. Okay, so data change which is the lowest, because it shows as data change. So these are 1 1. Okay, 1 1 at this point, and here it is 0 0. So this is 0 0. So here as well you'll have these 4 bits 0 0 and then 0 0 again here. So this because of 0 0 B. Okay, so we did 6 bits with replication as well as concatenation operator. So this can be printed as well. You can see this A is 1, so 4 ones, and then this B is copied over here. A is 0 4 times, and this is copied over here. So similarly 1 is copied, and then 0 0 is here. Okay, so this is 4 times A 0 0, and then this is copied over here. So this is a copy of replication, that is replication operator, and then concatenation operator. So the example of the 7 segment display, which is the next one. So there is a 7 segment display, A, B and C, D, E, F, G. Okay, so there are 7 segments in the in this display. Okay, so which are named as A, B, C, D, E, F, G, where module and the module name is segment 7, segment underscore 7. Input is given a number, a 4-bit number, which is 0 to 3. Output is going to be a 7-bit number. Okay, so 0 to 6 display. Okay, so if we give 4-bit number, and what should be that number? It should be displayed over here. So we know the output. Here I am declaring this as a reg because it's used in the always statement. Always, it's a behavioral description, and always at the rate num, that is input in the sensitivity list. So we are going to declare with a case begin and case statement. Case num is this. What is the number? If number is going to be 0 colon, that is a choice. 0 is a choice. What should be done? Display is going to be 7-bit binary 1 1 1 1 1 and 0. So that means this last one, this is going to be displaying 0, so only G is 0. So it is taking from A, B, C, D, E, F, G. So only G is 0, so remaining will be displayed. So this is display of 0. Okay, so it starts from A, B, C, D, E, F, and G is 0 here. Okay, so that is displaying 0. Okay, so the next case, suppose it is 1, B and C will be 1 and rest of them are 0. So 1, so B and C are 1 and the rest of them are 0. So for 2, A, B, G, E, D. Okay, so that's why A, B, D, E, G are ones, remaining this is I think you know this is for 1 and this is for 2, and then for 3 similarly the display for the choice 3 it is going to be A, B, C, D, A, B, C, D and then G. Okay, so this is 3. So similarly you can display up to, you can have even 4, 5, 6, 7, 8, 9. Okay, and then comes the default display which is going to be 7 times 1 bit 0. So just display 0. Okay, so if there is none of this, all of them made 0. I mean, display 0 in the sense it is all of them made 0, none will be displayed. Okay, so all 7 segments will be 0. That is the default case. So we need not stop here from 0 to 9. Okay, so the first 0, 1, 2, 3, 4, 5, 6, 7, 8, all of them will be 1. 9 again, this is A, B, C, D, E are 0, F, G are 1. So it need not be 1. You can even in hexadecimal we can display that 10 as A, 11 as B, and so on up to F. F we can up to 15 we can display, even we can increase this list to the another cases as well. If it is 10, then what should be the number 4 bit A, and it is 11, B, 12 and again C, and up to 15 it is F. So that could also, and then default case can become, if none of them were there, default case is display equal to 0, in the sense none of them will be displayed. So this is a behavioral description with a case statement. Okay, so this should end with end case and a default case also. This is end begin, which is ending over here. Okay, so test bench for it, 7 segment test. So inputs reg is again the in number, output is a display wire, 7 bit and this is 4 bit input. Integer I to have the numbers from 0 to 15, instantiate, call that module, the Verilog module 7 segment 7 UUT dot num and dot display. There are only 2 parameters in the input. Initial begin, let's see the display time, that is /t is a tab, number /t display. So just to arrange it in a nice fashion, dollar monitor within the quote dollar time number and display going to do that. So what is the initialize the inputs and after and add stimulus here. So in some of the examples we have seen at the bottom of the stimulus, it's possible to have it either at this place or in the stimulus as so. After stimulus for I is equal to 0, I less than 10. Okay, so here it can be up to 16 also. Okay, I equal to I plus 1, and similarly we have to give the conditions. What are the conditions for 10, 11, 12? Otherwise it would go to display of nothing. Okay, I equal to I plus 1 begin, a number equal to I. So whatever the I is generated, this needs to be declared as integer I and that is assigned to num. Okay, so these are all blocking statements. This needs to be, the loop is iterated, incremented every hash 10, that is 10 time units, and then end, this begin ends over here and hash 20 dollar finish. Okay, so after that it needs to be at some point of this should be finished. End, so end module, this end is corresponding to the previous begin. Okay, so before this integer over here you can see, so here this begin. Okay, so this begin ends over that, so the this is end module, the test bench stops over here. Okay, so now the waveform viewer or the waveform editor, how it gives that the number is given in this 4 bit, the expanded bits, every bit is shown over here, 0, 1, 2, 3, these are 4 bits. So first it is 0, up to this point, 100, after that 10 time units it is 0. Okay, it starts over I start incrementing. It is not known what is I in this for her first 100 nanoseconds, that is given global reset. After that the first time 10 time units it is 0. Okay, but the number is given as considered to be this is 0. Now the display, so it is giving the 0 up to this point. So actually our output starts from here. Okay, so 0, it is displayed 0, and then this is 1. Okay, for 1 B and C are 1, rest of them 0. 2 A B D E, yeah, G are 1, so you can see the rest of them 3 also, and 4 5 6 7 and then 8, all of them are 1, and then 9. Okay, we stopped with 9, so we can add some other choices also and get this up to 15. So 0 1 2 3, the I is get incremented every 10 nanoseconds. You can see 0 1 2 3 4 5 6 7 8 9 10. Okay, so we stopped over after 10, this 9 1, after that we stopped, and then so it is going to be a so here every 10, so 120 130 140 and so on. So you can see the increments which is immediately taking to number. Okay, I is increment is immediately substituted to the number. Okay, so this is about the 7-segment display. So the print or the $monitor statement with a different file or TCL console or log file you can store it. It can be saved in the TCL console or log file. So here it is giving 0 1 2 3 this is 4 5 6 7 8 and 9. The displays, corresponding displays are printed over here. That /t helps in, and the tab to display it in a nice fashion, this fashion. Okay. About it's again the combinational circuit with the behavioral description. So now comes to the priority encoder. You can say, suppose there is a input of A, B, C, 3 inputs. This is another example. So 1, and if input A is 1 and rest of them B and C, maybe it's unknown, X it is 0 or 1, any one of this, the output is 1 1. Okay, so next is if A is 0, B is 1. Okay, in that case C can be anything, 0 or 1. What is the output? It is 1 0. This is the code which is assigned here. Okay, and if A is 0, B is 0 and C is 1, then assign the code as or the output as 0 1. If all of them are 0, give 0. Okay, so now we just look at the priority structure. So if A is 1, irrespective of B and C, okay, so this would output 1. Okay, if B is 1, okay, then B takes the priority compared to C. If C is 1 and I mean the A and B if all the 3 are 1, A will take a priority. Okay, so among B and C, B will take a priority. So if you have A and C, then A will take a priority equal to 1. So this is how the priority is decided in the Verilog using the Verilog priority structure. So then immediately it should come to your mind that if else structure will be helpful to do that. Module priority select, this is module name, and the input ABC are 1 bit, output 2 bits, which is code. Okay, code are out here. What we have is 2 bits. Reg declaration, we are going to use it in the always block, always at A, B, A or B or C. So all of them are in the sensitivity list. Begin. If A equal to 1, first it checks with the if statement. If it is 1, code is 1 1 1. Okay, what is the next statement would be else if B equal to 1. Okay, so else if B equal to 1, output code is 1 0, 2 bit 0. If not, else if C equal to 1, this code should be 0 1. That is code equal to 2 bit 0 1. The code is used in for the assignment inside the always block, so it's declared as reg. And the next condition, else if one of them 0 0 0, code is going to be 0. So end here. Okay, so now we will see the test bench. The test bench of that module, there's a priority select test bench. So, you have the input, the inputs are A, B, C, and output we have 2-bit codes. Instantiate that module, priority select, you dot A dot B, this is with the port names dot A, and this A is local variable A, this within the brackets are local signals. The dot code, this is the code, it is representing the code. Okay, now the initial begin, the display ABC, and it is only displaying ABC, not the code. But in the waveform editor we can see, because output is declared in the case of module, so output will be automatically come in that waveform viewer. But when you want to print it in the console, you need to write it, you need to add out also here. Okay, so it's not added in this. Just to show you here, initialize the inputs ABC are 0. Now wait for 100 nanoseconds, and then we start adding the stimulus. Hash 50 A B again may retain that initialized values. After that, C is made 1. Okay, A B C, C is made 1, so C would be taking the priority, and then A B C, B1 C 0. So B is 1 anyway, that code will be selected. If here is the priority should be selected, which one will be taken as given the priority? B will be given the priority rather than C here. So similarly, this is also A equal to 1, it's clear the priority is given to 1, and A and C, among A and C, A will be given a priority. So among A and B, again A will be given a priority. So all of them are 1, A will be given priority. So because this is a priority structure. Okay. So now end. So let's see the viewer, what does it give? Okay. So waveform editor, which gives this ABC, the inputs, you can see it is up to 100 nanoseconds, and then another 100 nanoseconds we have retained this 0. Okay, here we made this, this is A is 0 0, B is 0, C is 1. Okay, C is 1, so it is selecting that 0 1. Okay, the code is 0 1. Here 0 1 0. Okay, so B is 1, the code is changing here to 1 0, you can see 0 1 to 1 0, and this is again 0 1 1. B and C are 1 and 1, so B is taking the priority, so still this is retained, so 1 0 is retained because of this. After that become, this is 1, A is 1 0 0, so A is taken a priority which is 1 1 1. Okay, this is 1 1 1 1 1. Okay, and then if you see here 1 0 1, okay, A and C, here again A is taken a priority 1 1 1 1 0. A among A and B, again A is taken as priority 1 1. So all of the 3 are 1, so then again the 1 1, so it's going to be 1 1. So 1 1 is retained over this period. Okay, the code, the output 1 1 is retained. So this is the expanded version of this 1 1, each bit, this is 0 0, this is 0 1 1 0 1 0 1 1, rest of the time all of them 1 1. So the priority structure uses the else if or if else structure. If what is the condition? Else if, what is the condition? If you use the multiple else if and else if, and it should be with stopping with else. Okay, so there should be an else condition. If there is if condition, then else condition should also be satisfied, even though multiple else ifs are there. So to avoid the avoiding the latches, okay, latch formation. So the outputs are printed over here. You can see this is 200,000. It is actually giving in picoseconds. 001. C is 1. So just whatever the inputs we had given there is displayed, not the quotes. Here it would be 0001, and then next is 110, and then rest of the cases it is 11. Okay, so this is 11, and when it is AB 001, it is going to be 01. Okay, so in these cases it is 0001. 0 is also 0. This is 10. 011, this is 10 again. Okay, and 100, it is 11. 1011, again this is 1111. So this is the output. If we want to keep, this is output is a code. Okay, so if you want to print, you can print it, not include. Suppose if you not include, then it's not, it doesn't get printed. That's priority selector, and then this is the example of the if else structure in the behavioral description. We use the always block for it. So, one 2 to 1 mux we have already done in the different 2 to 1 and 4 to 1 mux in the structural one. Also, we use the ternary operator. Here also we will be using the ternary operator D1, D2, 2 to 1 mux, and then this is data out. Enable bit is because this is going to be 1 bit. Data bit can be anything. So here we have chosen 2 bits, 2 to 1 mux. Input enable 1 bit, input is 2 bits, D1 and D2. Output is also 2 bits, and this can be 8 bit or anything. So assign simple data out equal to enable bit is 1, assign data 2. If enable bit is 0, assign data 1. So you can also check for the this is for the simple using the ternary operator, but bit size of the inputs can be, this can be 8 bit also, then data output will be 8 bits. So selecting the data, so this is simulated module, this module name is for the test bench. It doesn't take any inputs. The inputs which are defined in the module are enable and D1 and D2. The output is data out, which is 2 bits. Also data input is also 2 bit. Instantiate that module, the UUT enable D1 and D2, and this is with completing the instantiation. Next, give the stimulus, initial begin, display them, monitor with the initialize the inputs, and then add the stimulus here. So stimulus, which should be the enable 1, that time what is data 1, and enable 1 again what is data 2. So here itself we can specify also data 2, then it picks up that enable 1, that is D1, D2 is picked here. The D2 is not specified at this point, okay. So it would enable 1, D2 should be assigned, so it is 0 0, the previous value would be taken here. Enable 1, D2 is given here 1 1. So at this stage here enable is 0, so D1 is picked, here it's defined, fine. So let's see the viewer end module. So the viewer gives waveform viewer, enable is 0 over here, or 1, and rest of them it is 0. So the things, data input is 0 0 and then 1 0, and data 2 is 0 0 and then 1 1 here, okay. So these are expanded bits of data 1 and data 2. So data out is now here defined, this enable 0 in this case, and it should give the data 1. So this is 0 0, okay. And here data 1, the enable is made 1, but still the data out is going to be D2, whatever this 0 0, because it's not specified. The previous data 1, which is 0 0, is going to be taken. And when enable 1 is there, then data 2, yes, it is going to be 1 1 is picked up. And here again this is 1 1, and you can see the changes in the case of 1 0 as well. So enable is 0. So how this enable 0 is, enable 0 means data 1 should be picked up, data 2 is not there, then data 1 is not there, in that case the previous data 1 will be copied here as well. So this is 1 0. So the data out print of the 2 here is 0 0 1 1 and 1 0, the data outs corresponding to it. You can see this is picked up from here, this is picked up from here, and here it is 1 0 from here, okay. Data 1 0 and this is 1. So these two are taken at the here 1 1 1. So 2 to 1 mux output, you can view it here in the data out. So we had looked into the simulation of this, all the combinational logics. So we had given the details of the assign statement, always block, and structural model, instantiation of the various components has been we have learned in the structural model. What is the data flow model, how to develop a data flow model using the assign statements, and how the behavioral description can be used to develop the behavioral model using the always block. And the sensitivity list gives the behavior of the model. So always at the rate what is in the sensitivity list, whenever there is a change in the signals, the behavior change, is observed using the always block. So it's behavioral description, and in the assign statement is continuous statement when the right side expression is continuously evaluated and assigned into the left hand side. Okay, in the assign statement. Structural one, we have the different structure. Instead of a function, we just look at the structure, how it is connected, and keep instantiating. Either it is a built-in gate or any circuit which is defined on your own. So this is about the digital circuits modeling in 3 different Verilog modules, and we'll be for the we dealt only the combinational logic circuits. We'll be moving on to the sequential logic circuits in the future lectures. Thank you.